Hello, my name is Dane Osterberg.
Hello, my name is Edward.
Hello, my name is Justin Zemer.
Hi, I'm Justine Tambo.
Logistical concerns, rapid mobilization, and the deployment and operational capacity is often an issue that our responders face. It sometimes leads to an increased loss of life. So the proposed design focuses on targeting initial rapid response in an emergent situation. It can take up to several days before the initial response is complete, which is too long for people in a disaster to wait. So rapid responders are going to be our direct customers. However, the local governments will be establishing certain policies to allow for the use of the design, making them the indirect customers. Taxpayers are also the indirect customers since this design is used to save the lives of civilians. So our design requirements were created around what rapid responders were actually needed in order to accomplish their mission. So our design meets all of the following design requirements. Now I'm going to turn it over to Justine, who's going to talk about our robots.
Our disaster response robot swarm consists of 4 robots: supply delivery, atmospheric sensor, firefighting, and survivor locator. The supply delivery robot, designed by Edwin, delivers supplies to first responders and other robots. The atmospheric sensor robot, designed by Daniel, detects, locates, and communicates hazardous gases, fires, and survivors. The firefighting robot, designed by Justin, detects, locates, and fights fires. The survivor locator robot, designed by Justine, searches for and transmits survivors' locations. Now we'll start with Daniel to describe his atmospheric sensor robot to us.
Atmospheric sensing robots designed to detect toxic gases, find fires, and locate survivors. So let's see how it works. Mechanical design shows all the sensors on board, starting with the distance sensor that also acts as an altimeter, the infrared sensor used to locate survivors, temperature sensor, gas sensor. Everything's powered by circuitry and an Arduino. It also has a communications suite with antennas to talk to the central hub. It has 4 propellers for in-flight quadcopter capability, as well as track drive for ground operations. Circuit design, everything's powered by 9 volts. The circuitry up forward controls the 4 DC hobby motors for track drive. The chip here is the flight control for 4 DC motors and propellers. The temperature sensor, gas, and infrared sensors, as well as a distance sensor with its associated servo that moves it up and down for altimeter mode. For the flow chart, everything's based off of commands received from the central hub. The first 4 commands deal with the track drive capability to move it forward, left, right, stop. The next few deal with the in-flight capability to take off, land, ascend, descend, yaw, left and right, etc. And finally, the sensor suite to turn on its gas, temperature, infrared, and distance sensors. Let's look at the actual code. Starting from the top, we initiate all our variables. As we enter the loop, the serial.available continuously monitors the serial monitor, looking for any commands from the central hub, and will execute functions as necessary. When we get to the function, this is where we define the actions. To get altitude, we can, all our drive commands, drive forward, backward, stop, turn left and right. Our flight commands to take off and land, fly forward, yaw, left and right, hover, ascend to specified altitude, descend to specified altitude, and finally our sensor commands that allow us to activate any of the onboard sensors to get the temperature, detect gas, and distance. These are command prompts we're going to be using to simulate commands from the central hub. So we'll start off the simulation by driving the robot forward. We'll see that it engages our DC hobby motors. If I turn right, the right side will reverse, allowing us to turn. Same thing with left. When we take off, you'll notice these will stop and our propellers will turn on, and it's going to climb until the sensor altimeter reads 10 inches, and then it'll begin to hover. We can further ascend if we wish to a specified altitude of, let's say, 25 inches, and it will continue to climb until the altimeter reads 25 inches, in which case it'll stop and hover. Let's look at our sensor suite now, starting with the infrared capability to define our survivors. It's going to look for any heat in the area, and it's found it, so it's going to request survivor locator on scene. The temperature is going to be used to find any temperature above 200 degrees Fahrenheit. In this case, it's below, so let's increase it a little bit. And we'll see if it finds there it is, a high temp alert. It's going to automatically fly an expanding square pattern so it can find the highest temperature in the area and then reports that. So I increased the temperature a bit and it reported that higher temperature. And finally, the gas sensor, if we're flying through a toxic gas cloud, that's going to detect that it's above a nominal level and report that and request assistance from the survivor locator bot. This concludes the demonstration of the atmospheric sensor. Edwin will now talk about his supply robot.
The supply robot's main purpose is to replenish supplies in the crisis area. It has the ability to assess the current supply levels of first responders, as well as accept commands to replenish specific supplies. The supply robot's mechanical design comes with a pair of versatile motorized forks for lifting and holding supplies, a sensor tower for its multiple sensors, as well as a thread powered by 6 wheels for movement. The supply robot circuit design includes 6 motors to power the robot's 6 wheels for mobility, 2 ultrasonic sensors for avoiding debris and other types of obstacles, as well as a passive infrared sensor for detecting movement and avoiding collisions. Communication with the central hub enables the supply robot to accept requests for supply replenishments, as well as assessing supply levels for the various active first responder units. The supply robot's behavior once in a disaster area checks for any active request, and if there is, it attempts to fulfill it. Otherwise, it assesses the supply levels of the first responder units and replenishes any that may have run out. The supply robot's behavior depends on its 2 ultrasonic sensors and a passive infrared sensor to avoid collisions and maneuver to its destination in order to accomplish its task.
So for the firefighting robot, it finds fires, fights fires, and reports fires. For the mechanical design, for the gear motors, Arduino circuit board, some power supplies, a servo in the middle, a spray nozzle on the front, a temperature sensor on the front, as well as an infrared sensor and also an ultrasonic distance sensor. And those are the dimensions. And then the top right picture, you can see on the back that I have the plug for refilling the tank once agent is empty. For the circuit, there's an ultrasonic distance sensor, a force sensor, a temperature sensor, an infrared sensor, a low pressure on, 4 hobby gear motors, and valve servo to actually a firefighting valve. So the firefighting robot, it'll commence an algorithm, and the hub is presented between the hub, and it goes into the hub. And it also has room for an ultrasonic sensor, seeing once the pipe actually is or not, and then sending an ascend command, a descend command, a hand left command, or a hand right command if that's necessary. And then also for the sensors, the algorithm, some temperature sensor constantly to the central hub. They're also send infrared to the hub and pressure data to the hub. And if the pressure sensor is 0, it will sound a pressure alarm, and then it will cause the robot to return back to the hub. And if the hub is sending a fire detected, then the robot will commit spray. And here I'll scroll through my code and start at the top here. There's all of the residues here. They're defined everything. Someone set up another way of getting your value. Here's for the ultrasonic distance sensor. If I lower that to less than 5 inches, you can see that the atmosphere load is shifted. 2 piles through the robots move backward, up and back and forward. Back up to 12 inches. And then down here, keep going. There's a couple of conversions for pressure for the pressure sensor. So the pressure sensor, if you roll it all the way down to 0, it will cause the alarm to go off. And then you keep going down, and we have all of our command functions. So if I detect 1, it would cause the robot to turn left. It'll take a second here for it to catch up. Also, you can see the temperature and pressure and distance from your phone distance sensor are constant and displayed and sent to the central light. As you can see, the hobby gear motor shifted, and I started again. It's 0 printed turn left, and it'll also print another very important command, which is command 7 to open the actual valve servo. So once valve 7 is tight, it'll shift the valve servo to top right to the 180-degree position. There's also the infrared sensor down here, and as I change temperature, you can see that it will change the temperature. Once you see the valve servo just change to actually its correct. But it change the temperature a little bit more. You can see that. And you can see temperatures changing in the servo monitor display. And now we're going to turn it over to Justine, who's going to talk about survivor locator.
Thank you, Justin. I will now present the survivor locator robot. It is designed to locate survivors, avoid obstacles, and it has a retractable mast to avoid overhead obstacles. It has ruggedized tracks, so it can go off-road. It has a distance sensor in a mast, a temperature sensor in the mast, and then 3 distance sensors in the front of the body. Shown here is the front, left, and right distance sensors. This is the mast distance sensor, which is tied to the servo motor to raise and lower the mast, the gear motors to power the wheels, and then the temperature sensor shown here on the breadboard, and 9-volt battery to power the motors. Flow chart for obstacle avoidance. We will measure the front distance. If we never see anything within 20 inches of the front distance, we're just going to keep moving forward. If we do see something within 20 inches of the front sensor, we're going to measure the left and right distances, and then basically the side that has more clearance is the side that we're going to move to, and then we're going to keep going back and measure the front distance and so on. Then the mast retraction, we're just going to measure the distance sensor on the mast. If something is shown within 20 inches of the mast, it's going to retract the mast and then go back to measuring. If we never see anything within 20 inches of the mast will stay up, nothing will happen. The temperature sensor is looking for objects between 28 degrees C and 45 degrees C, which translates to 82 and 113 degrees Fahrenheit, which is a good scale for live humans. If we find something within that range, we're going to alert the hub. If we never find anything in that range, we just keep measuring. Here is my code, and I will move and show the code within Tinkercad in simulation mode. So let's see, here is my front sensor. If the object stays further out than 20 inches, and we just keep moving forward. If it comes within 20 inches, then we're going to look at the distances of the other two, the left and the right. So we have more room on the right, so we should be turning right. And then if we switch it, then we'll be turning left. This is the mast sensor. Let's see, if we come within 20 inches, then the mast will lower. You'll see the servo motor release and retract the motor, the mast. And let's see here. Here we have our temperature sensor, and if we put this in between that 28 and 45, we will see we were locating the hub as a potential survivor located. And now Daniel will share the collective behavior of our swarm.
The central hub is critical to the operation of our swarm. When the swarm is first deployed, the central hub will initiate 3 robots: the atmospheric sensing, the survivor locator, and the firefighting robots. When the atmospheric sensing robot's initiated, it will report to a position requested by another robot or that the operator chooses from. Turn on its 3 sensors, and if toxic gas or a survivor is possibly located, the central hub will order the survivor locator robot to that position. If the atmospheric sensor detects a high temp, the central hub will order the firefighting robot to its location. When the survivor locator is initiated, it will report initially to a position requested by another robot or that the operator chooses from. Turn on its infrared sensor and attempt to find a survivor. If a survivor is located, it'll alert the central hub and begin first aid. If the first aid supply is low, the central hub will order the supply robot to its location to resupply. Once first aid is complete, the survivor locator will evacuate the survivor back to the hub. With the firefighter robot, once it's initiated, it reports to a position requested by another robot or one that the operator chooses from. It turns on its temperature sensor to find the fire. Once the fire is found, it'll begin to fight that fire. If the low pressure alarm is detected, indicating that the water level is low, the central hub will order the supply robot to the scene in order to resupply. Once that fire is out, the central hub will then order the firefighting robot back to the central hub. Now Edwin will summarize our project.
Disaster response is dangerous and unpredictable and constantly evolving. As such, our line of robots were designed to be easily deployable and effective in the most extreme environments. Their focus is to expedite and assist human-led search and rescue efforts, with emphasis on keeping first responders and survivors safe. It can be successfully implemented in a wide range of disaster scenarios. They are durable and designed to be effective, high quality, and low cost. Our line of robots consists of a supply delivery robot for replenishing supplies in the crisis area, a firefighting robot that finds fires, reports it, and attempts to extinguish it, an atmospheric sensing robot that detects and locates the more volatile areas of the crisis zone and reports it, as well as a survivor locator robot which detects survivors and transmits their locations to the first responders.